Hello everyone, very pleasant good morning to one and all. Myself Dr. Amjad Basha, Assistant Professor in the Department of Mathematics, the new college. In this lecture series, I am going to discuss about types of grammars. There are 4 types of grammars in Chomsky hierarchy. Type 0, which is called as unrestricted grammar. Unrestricted grammar. It is recognized by Turing machine and the other one is type 1. The second is type 1. Type 1 is called as context sensitive grammar. Context sensitive grammar, and this is accepted by linear bound automata. Linear bound automata. First one is unrestricted grammar, and this is recognized by Turing machine, and this type 1 is context sensitive grammar, and it is recognized by accepted by linear bound automata. Type 2 is context free grammar. Context free grammar, and this is accepted by push down automata. Push down automata. And the last one is type 3 grammar. This is regular grammar. Type 3 is regular grammar, and it is accepted by finite automata. These are the 4 types of grammars: type 0, type 1, type 2 and type 3. The languages which are generated by these grammars are recursively enumerable languages. The language which is generated by type 0 grammar is called as recursively enumerable languages. The language which is generated by context sensitive grammar is called as context sensitive language. The language which is generated by context free grammar is called as context free languages, and the language which is generated by regular grammar is a finite regular language, and which is accepted by finite automata. Now let me discuss about each and every type of grammar in detail with illustration. Phrase structure grammar. A phrase structure grammar is a 4-tuple. A phrase structure grammar is a 4-tuple. Phrase structure grammar is a 4-tuple. That is, G is equal to Vn, Vt, S and Phi, where Vn stands for non-terminals, Vt for terminal symbols, S is a special non-terminal symbol which is start symbol, and 5 is set of protections. 5 gives set of protections. Is a 4 tuple. As I told you, in this we'll be using alpha tends to beta, in which is called as the protection rule or rewriting rule. We'll be using alpha tends to beta. This is called as protection rule or rewriting rule. This non-terminal, terminal, start symbol and set of protections together gives a complete structure of grammar. So each grammar, whether it is context-free, context-sensitive, regular or unrestricted grammar, each grammar, all these 4 types of grammar has its own structure which denotes the way how the language has to be generated. So we'll be discussing now each and every type of grammar with example. Let me start with a context sensitive grammar. Context sensitive grammar. A context sensitive grammar contains only protections of the form alpha tends to beta, where this denotes the length of the string alpha less than or equal to beta. Okay. Here alpha and beta in the protection can be expressed as alpha and beta in the protection alpha tends to beta can be expressed as alpha is equal to phi 1a phi 2 and beta is equal to phi 1 psi phi 2. Alpha are possibly empty. Sometimes alpha and or phi 2 are possibly empty. In the case of context where your psi is absolutely non-empty. These are the conditions to be satisfied to generate any context sensitive grammar. The language which is generated by context sensitive language is A power n, B power n, C power n, such that n greater than or equal to 1 is generated by the following grammar. Let me take a grammar G in which the non-terminal set of non-terminal I have is S, B and C. Similarly, terminals A, B, C. My start symbol is S and my phi is set of protections. So I'll be having different start symbol A capital S, B, C, and the other start symbol is A capital B, capital C, and the other protection CB as BC, then AB as AB, BB as BB, then B capital C as B small c, C capital C as CC. These are the different protections of the context sensitive language. So how to derive these steps? Suppose if you want to derive the first word of this, capital S, you can take this as A capital S B C. Generating first word is very simple, so let me move on to the second one so that I can generate A square B square C square. Then this S will be replaced as, again, this I can rewrite as AA BC BC. Okay, this S is replaced by ABC. This S, again this starting symbol, I have replaced it with ABC. This A remains same and BC remains same. So again AA B B C C. So what we have done here is that BC, B is replaced by, look here, I have CB can be replaced as BC. This CB I have replaced by BC. Then C remains same. Similarly, what I will be doing is AA B small b capital B CC. In this case, what happens is that which protection is being used? Capital B small b capital B. Okay, AB is replaced by A capital B is replaced by AB. That protection is being used here, so that I need AA. So having that in mind, I have generated AA B capital B CC. Again, in the next case, I have AA BB capital C. Here what I have done is that B and small b and capital B is replaced by BB. Again, in the next case, I have AA B B C and capital C. Then I have used this B capital C, I have replaced this B capital C with B small c. Then finally what I will be doing is C capital C will be replaced by two small c's, that is AA BB CC. So finally I could generate the word A square, B square and C square. You could notice here that finally I have obtained the word A square, B square, C square. So if you continue like this, you can generate different words of this language such as A cube, B cube, C cube, A power 4, B power 4, C power 4. You just keep replacing with the given set of protections, you will be getting different words of this language. Okay, so above this you can even have ABC as well. So by using this set of protections, all possible words of this language can be generated. So next we will move on to another grammar, which is context-free grammar. So when it comes to context-free grammar, it contains only protections of the form. It contains only protections of the form alpha tends to beta, where your length of alpha should always be less than or equal to the length of beta. Alpha belongs to non-terminals and beta has the form and beta has the form A capital B or A, where A belongs to terminals and B belongs to non-terminals. If these conditions are met, you can generate context-free language. Please we'll have a look at this example as well, in which we'll be generating context-free grammar with the help of these conditions. I repeat, the context-free grammar has only protections of the form alpha tends to beta, where the length of the alpha should always be less than or equal to beta, and your alpha belongs to non-terminals. Alpha will always take non-terminal symbols, and beta has the form AB or A, where A belongs to terminal or B belongs to non-terminal. Okay. The language which is generated by context-free grammar is A par n, B A par n, such that n greater than or equal to 1, for which the grammar is SC. We have two non-terminal symbols in this, and S is a special symbol which is used as a starting symbol. Then followed by two non-terminals, which is AB and start symbol as S and phi as set of protections. We'll have a look at the different types of protections which is being used over here. Phi is set of protections. The protections are S tends to A capital C A, then C as capital C as A capital C A again, then C as capital C as B. Okay, these are the three protections we have to generate any context free grammar. So how the words could be in this grammar? It can be ABA, it can be A square BA square, it can be A cube B A cube, it can be A par 4 B A par 4. These are the different words needs to be generated using this set of protections to generate context free grammar, to generate context free language with this context free grammar. Let me generate some words here. Suppose if I want to generate A square B square B A square, the protection I will start it as S as A capital C A followed by A C A. The protection which I have used is, look here, I have replaced C as ACA. Okay, if you replace C as ACA, what will happen? C as ACA. This I have replaced this C as ACA. If I want to stop with this just one word, I can have AA. Now C I'll replace it by B, so I'll just get AA then. So the word which is generated over here is A square B A square. Similarly, if I want to generate A cube B A cube, then you will start with S as A capital C A. Then again you will replace your C with ACA. ACA. C is again capital over here. Okay. C I'll replace this ACA. Then this A will come as it is. Again, if I want, what I can do, n number of times I can just keep repeating it. So again I'll replace this C as ACA. A.C.A, you will have A here. So if you want to end up with A cube, B, A cube, now C will be replaced by B. Therefore, A, B, A, you will be getting. That is A cube, B, A cube. This is the word which will be generated now. So if you continue this process, you will be getting different words of this language. So finally, you will be getting the language as mentioned in the previous slide, A par n, B A par n, such that n greater than or equal to 1. This is an example for context free language.